In 2023, astronomers heard the universe hum, using nothing but the ticking of dead stars spread across the Milky Way. How do you detect a gravitational wave that takes years to complete one cycle? Ground-based detectors like LIGO listen to fast waves, tens to hundreds of cycles per second, with 4-kilometer laser arms. The newly reported signal sits down at nanohertz, one oscillation every 5 to 20 years. You can't build an instrument with arms measured in light years. So, pulsar timing arrays turned millisecond pulsars into the endpoints of a galaxy-sized detector. We time those pulses for decades and look for coordinated drifts measured in nanoseconds. If that hum is real, it's the combined murmur of supermassive black hole pairs born in galaxy mergers. How can a dead star tick steadily enough to notice that? The answer is that some pulsars are absurdly stable rotators. A millisecond pulsar is a neutron star about 20 kilometers across, spinning maybe 600 times per second, and its radio beam sweeps past Earth with nearly the same rhythm for decades. Radio telescopes timestamp those pulses, then subtract everything predictable: Earth's orbit, the solar system's motion, and delays from interstellar plasma. The leftovers are timing residuals, how many nanoseconds early or late a pulse arrived compared with our best model. For the cleanest pulsars, residuals can be 30 nanoseconds, about 9 meters of light travel distance, but each pulsar has its own quirks: tiny spin noise, occasional glitches, and propagation changes in the plasma between stars. With all that mess, what stops us from mistaking random drift for a gravitational wave signal? What stops us is correlation. A pulsar timing array, a PTA, times dozens of millisecond pulsars, maybe 30 to 70 of them, for 15 years or more. A gravitational wave passing Earth stretches space in one direction and squeezes it in the perpendicular, so pulse trains from different parts of the sky speed up or slow down together. That means we don't look at residuals one by one. We cross-compare every pair. The gravitational wave signature is a specific angular fingerprint called the Hellings-Downs pattern. Nearby pulsars share similar residuals, while widely separated pairs match less, and around a right angle, the correlation can even dip negative. In 2023, multiple collaborations reported this pattern emerging. The leading source is a background made by supermassive black hole binaries, hundreds of millions to a few billion suns, orbiting with periods of years. But what, physically, is a wave doing to make a pulse arrive early? The answer is that a gravitational wave changes space-time along the radio pulse's path, so the pulse rate you measure shifts by a tiny fraction. That fractional stretching is called strain. For this background, it's about a quadrillionth. Over a 5-year wave cycle, that tiny rate shift accumulates into tens of nanoseconds of timing residual. Some of that comes from the wave passing the pulsar thousands of years ago. That pulsar term has a different phase for each pulsar, so it won't correlate. The shared piece is the Earth term, the same ripple passing the solar system now, and that's what produces the Hellings-Downs pattern. It even forces you to know the solar system's center of mass to about a meter, because an ephemeris error can mimic a wave. Stepping back, an observatory the size of the galaxy. No mirrors, no lasers, just clocks. Now the hum has a fingerprint. We can ask, is it really black holes? And can we do astronomy with it? The background has a spectrum. Different pitches correspond to different orbital timescales, so its shape tells you how supermassive binaries lose energy. If stars or gas are helping drain their orbits, the spectrum shifts, which feeds straight into our story of how galaxy mergers end. With enough pulsars, the background can break into individual sources. One nearby binary would leave a clean, multi-year sinusoid in the residuals, letting you hunt a host galaxy. And if the spectrum doesn't fit black holes at all, it becomes a constraint on exotic sources like cosmic strings. The improvement plan is simple: more time and more clocks, 15 years to 25, 50 pulsars to a few hundred with the square-kilometer array. Slow motion, but real discovery. And that brings us back to the strange claim in the opening: we heard the universe without a microphone. Here's what actually happens. As a nanohertz gravitational wave passes, it stretches space along one axis and squeezes it along the other. That changes the light travel time of each pulse by a few meters, which shows up as a few tens of nanoseconds in our arrival time data. We heard the universe hum because gravitational waves slightly shift pulsars' tick rates in a shared skywide pattern. The wild part is the timescale. These waves were launched by black holes orbiting each other when galaxies merged, and a single oscillation can take a decade to wash across the solar system. Keep timing long enough, and we won't just detect the background. We'll start pointing to individual binaries and watching their orbits tighten year by year. What other cosmic rhythms are hiding below nanohertz, where one cycle lasts longer than a human life? Like, if this was interesting, hit the subscribe for more and turn that notification bell on.